Okay, so first I'd like to talk about Simpsons Paradox. How many of you have heard about this? Okay, you have heard about it?
It was one of the problems.
Oh, it's one of the problems in the, okay. So it's one of the suggested problems, actually.
But I didn't understand it.
I see. Okay, so hopefully you'll understand it now. It's very interesting. I find it very interesting. So basically, the idea is that we have two subgroups. Here we have the blue group and the red group, right? And we have basically two variables, right? So x and y are two random variables, right? So we can think of x as, for example, getting somebody vaccinated, and y as, how much symptoms they have if they get COVID, right? Or x can be the dose of a drug that you give to somebody, and y can be how much they live after they are diagnosed, right? So x and y are two different random variables, right? And blue and red are two different populations within our samples, right? So you can think of blue as, for example, older adults who get the vaccine, and red as younger people who get the vaccine, right? So two different classes of the people who are under study, right? So the idea is that if you look at the blue individually, you see that as you increase x, y also increases, right? Same with y, right? Same with the red color. So we see that as we increase x, y also increases in the other group, right? So remember we talked about correlation. When we calculate correlation between x and y, for the blue group, we are going to get a positive correlation, right? In this case, the correlation is probably going to be 1, a very large number, because it's a perfectly linear relationship, right? So we can see that in this subgroup, x and y are positively correlated. Same in the red group, right? But let's say that you ignore the fact that these are two different groups, right? And analyze the entire samples together, all of your samples together, right? Now the trend reverses, right? Now what we see is that as we increase x, y actually decreases, right? So here the trend is this dashed line, right? And that is the Simpsons paradox, right? And it's very, very counterintuitive. And it's very easy to fool people, right, using Simpsons paradox. I will tell you some tricks, and you will see that, if the person doesn't know the trick, it's, super easy to fool somebody into thinking whatever you want the person to believe in, right, using real data, right? So I got this data from this website. So it's a website that gathers data from on COVID, right? So people who were hospitalized in Canada from December to November of this year, and people who are unvaccinated, and people who are fully vaccinated, right? So I was trying to, so the issue with this data is that this data starts from December 14th, and at that period, vaccines were not available, right? So one reason that we have a large population here is that for a large period during this time, vaccines weren't available, right? So we can't really fairly look at this data and say that, oh, the number of unvaccinated is, many, many more than vaccinated, right? And I couldn't actually play with the data, so it doesn't allow you to select the range, right? So to make sure that, for example, you select the range between August of this year and November of this year. So since August, many people have been vaccinated, right? So it doesn't let you do that, right? So instead, I started searching, and I found this basically article on CBC that I found is the closest thing that I want, right? So the good thing about this article is that it's in New Brunswick, where COVID started, they didn't have any COVID cases for a long time, right? So when there was no vaccine, they didn't have many COVID cases either, right? So they have 84 deaths so far. 17 of them were fully vaccinated, and the other 67 were unvaccinated or partially vaccinated, right? And another nice thing about this article is that it mentions that by April 1st, when the shots became available to age over 75, 30 people had already died, right? So we can safely subtract these 30 from these 65, right? Because what we can do is that instead of looking at the total deaths since beginning of the pandemic, we can look at the total deaths since April 1st, right? Because April 1st is the date where vaccines started to become available. I was trying to find a later date, for example, August 1st, when actually more people, this is the date that vaccines were available, right? But very few people were actually vaccinated by this date, right? But the website doesn't have that info, right? So basically everything in black is from this article, and the text in red is my own. So we can say that since April 1st, 17 people who were fully vaccinated died, and 37 people who were not fully vaccinated died, right? So does this mean that vaccines are 37 divided by 37 plus 17, or 68% effective, right? So can I say that, look, 17 people who were fully vaccinated died versus 37 people, right? And I'm going to say that, I'm going to divide those and say that 68%, the vaccine effectiveness is 68%, yeah.
So the first deaths, were they by age of over 75? Because you removed 30 people that died over 75, but the first of 67?
No, this is not, no, so you can forget about the age over 75. Basically, by April 1st, 30 people had already died, right? So I was trying to, we can forget about this age 75. Basically, this line is just, I didn't want to look at the data since the beginning of the pandemic. I wanted to look at the data since people actually could get vaccinated, right? Because early on, imagine that the pandemic was going on for 10 years, right? And in those 10 years, vaccines weren't available, right? So that's clear that many people who are unvaccinated die because vaccines are not available, right? So I was just trying to find a more recent time. But your answer is right. It does have something to do with age. Yeah.
So that 30 people die is like they are fully vaccinated, or no?
No, these 30 people, of course, weren't fully vaccinated because by this date, vaccines weren't available at all, right? So these 30 people, of course, were not fully vaccinated because by April 1st, nobody was vaccinated. Yeah.
Well, the thing is, though, is that your criteria for saying effectiveness, you're just saying that a person has to survive for the vaccine to be effective. But is that really what we're basing it on?
So yeah, so I'm basically saying that, the vaccine is effective. What I will do is that I will divide. So for example, if this number, 17 people who were vaccinated, was actually 0, for example, right? Then the number that I would get is 100, meaning that the vaccine is 100% effective, meaning that nobody who's vaccinated can die, right? So I'm defining effectiveness myself. I'm defining it as the number of people who weren't vaccinated divided by total number of deaths. That's my definition. It's not a perfect definition, but that's how I define effectiveness, right? So if 17 was 0, I would get 100% effectiveness. Yeah.
So I'm guessing, relating to the Simpsons Paradox, it's just saying that right now you're basing it on all age groups,
yeah,
rather than just specific age groups.
Exactly. So that's one very important criteria, right? So when you look at, for example, the number of hospitalizations, right? Right now, if you count, I don't know this data, I really searched for it, but I couldn't find it in Canada, right? But I imagine that the number of hospitalizations would be something like 40% of all hospitalized people from COVID are vaccinated. That's my guess. I'm not sure, right? But the reason for that is that almost all of the people who are above the age 65 are vaccinated, right? And those people are very vulnerable, right? Whereas people who are very young, right? People who are, for example, 15 years old, many of them are not vaccinated and they are not at risk, right? So that's one very important reason. So basically the answer is in many, many different basically points. First of all, my computation in the previous slide was incorrect because first of all, 80% of eligible Canadians are around 80% are vaccinated. That's the vast majority, right? So you just have more people who are vaccinated. Of course, you are going to have more people from this group who are also hospitalized, right? So the first thing you have to do is that you have to normalize by the vaccinated population, right? And the other point is that most of the people who are vulnerable are vaccinated because they are very worried, they get shots. And many young people who are not worried at all, they think that they have a good immune system, they don't get the shot, right? So they are not vulnerable to begin with, right? So it's not fair to compare vaccinated versus unvaccinated people because most of the people above 65 are vaccinated, whereas not most of the people above 12, like between 12 to let's say 30 are vaccinated, right? So I basically made up some arguments quite similar to that. So let's look at the stat of the people who go to hospitals and die, right? So I made up some number. Let's say if you look at some, critical ward of the hospital, 10% of the people who go to hospital die, right? And if we compare that to people who go to some fat, greasy burger shop, that's only 0.1% of the people die after a year, let's say, of going to some burger shop, right? So based on this statistic, can we say hospitals kill people? No, because the population of people who go to hospital are already sick, right? Whereas the population of the people who go to burger shops are not necessarily sick people, right? And, I made it up so that it's very obvious. Very often it's not obvious. It's very subtle, right? And many people don't get the idea that, when you treat statistics, you have to look at the population that, was basically treated for different drugs, right? So based on that, we can look at the same curve again, right? So here assume that Y is the number of years that some patient survives, right? And X is the dose of a drug that you give to the patient, right? And assume that blue is young patients where, where you basically, you don't give them, a lot of, you just give them a little bit of drugs, right? So because for whatever reason in your study, you decide to give the younger people less dose. And you decide to give the older people a higher dose because you think that they need a higher dose, for example, right? So here, when we look at the younger people, again, we see that, the higher the dose that you give them, the higher survival rate they have. Same for the older people. But when you look at everything together, right, you clearly see that the trend reverses in the other direction, right? And, if you have a drug manufacturer and you want to, fool authorities to think that your drug is good, you can design your study other way around, right? To give certain doses to certain populations who are not at risk and other doses to basically, even before you do the study, you're sure that your drug is going to work, right? Based on how you designed the study. So these are the things that, the boards that approve drugs are very careful about, right? These are very subtle things in statistics that, if you design a study, you have to be careful about, and if you are studying a study, you have to be careful about as well. So I found another interesting thing about Simpsons Paradox in COVID. So this is a new paper that's published in IEEE Transactions on AI. And they basically looked at these guys, they looked at the statistics of case fertility rates in Italy versus China, right? And they found out that the fatality rates in Italy, they are less than China in all age groups, right? So the orange color shows Italy, and the blue colors shows China, right? So we see that in Italy, less percentage of people die from COVID compared to China in all age groups, right? Above 80, between 70 to 80, and so forth, right? So Italy has a lower case fertility rate for all age groups. But when you look at all the population, the trend reverses, right? So if you look at the entire population, then Italy has a much higher case fertility rate compared to China. And that's very, very, I see some faces that, are very confused, and that's how I was. Before reading the paper, I tried to find out what's going on, because this doesn't make sense to me at all. And the title of the paper is Simpsons Paradox in COVID-19, right? So I knew that it's related to Simpsons Paradox, but I couldn't figure out what's going on. It's very counterintuitive that in all age groups, Italy has a lower case fatality rate, but overall it has a higher fatality rate, right? So maybe you guys are smarter than me. Any ideas what happened? Yeah.
It's actually kind of similar to one of the practice problems at like the very beginning of the school year.
Okay.
Where just due to the sample size, there's probably just more deaths by age group in China, and because there's a lower population in Italy, like that might.
It's not to do with the lower population in Italy, but it has to do with the other thing that you said, in the proportion of the fatalities in different ages, right? So any other ideas what might be going on? Yeah.
Maybe they calculated more like elderly people versus younger people.
Yeah.
For certain parts of the graph, I guess.
Yeah.
And the total they took. It makes sense in my head, but I don't know what I expected.
Yeah, so what happened is that in Italy, they had more in this group, right? So there were more elderly, deaths in Italy compared to China. And since the fatality rate in elderly is higher, then basically the overall rate was higher. So basically, the graph at the bottom should make things more clear. So the graph at the bottom shows proportion of confirmed cases by age group, right? And we see that in China, the confirmed cases are mostly in the younger age group, right? Whereas in Italy, there's a large proportion of patients who are at the oldest age group, right? Plus 80 and 70 to 79, right? So basically we have more older patients in Italy. And these basically older patients led to this overall larger fatality rate in Italy compared to China, right? So imagine that, we have, like in these groups, imagine that we have 100 patients in Italy here, 100 patients in Italy here, but in other age groups, we have fewer patients, in Italy. And remember that it is correct that plus 80, the fatality rate is higher in China, but there are fewer total people who actually were diagnosed in this age range, right? So yeah, this number is large, but it's multiplied by a small number because there is a small proportion of people in this age group who were diagnosed, right? Whereas in Italy, many people who were diagnosed, they were very elderly, right? And this basically led to this larger larger case fatality rates in Italy.
Shouldn't you want like each age group have the proportional have the same number of samples?
So basically here, what we do in this graph at the bottom is that, let's say in Italy we have a total of 1,000 patients, right? 1,000 people who basically were confirmed to have COVID, right? So here what we are doing is that we are seeing that 20% of those, which is 200 of those, are above 80, 200 of those are between 70 to 80, around 200 of those are between 60 to 70, and so forth, right? So this graph shows distribution of patients by age, right? So here we see that out of those 1,000, Italians, many of them were old, and the blue curve, it's not necessarily 1,000. The blue curve could be, 10,000, could be a different number. But in both cases, we are dividing by so these are percentages, right? So here in China, we see that most of the confirmed cases were younger people, right? I don't know if I answered to your question. Okay, so before I mentioned the second part that case fatality rate is lower in Italy for all different age groups, I'm sure you would have assumed that overall it also has a lower case fatality rate, right? But that's not the case, right? When you divide something into multiple groups, you can't simply group them all together and look at them as one group, as we saw in the other graph, right? So here we see some trend here, we see some trend here. If we look at everything together, the trend actually reverses. Right? Okay. So statistics is a very, very difficult concept, right? And it's very important that you pay, close attention to the concepts behind the numbers. Okay, so let's continue solving sample questions. If there's no questions. Okay. So consider the null hypothesis is that the average weight of male students in a certain college is 68 kilograms. The alternative hypothesis represents that it is unequal to 68. Basically less than 67 or more than 69, right? So this is 68 and 67, 69. So if we are here, we reject H0, or we are here. Assume standard deviation of the population is 3.6 and a sample size of 36. What is the type 1 error, right? So basically, we want to calculate the type 1 error, which means that we basically fail to reject the null hypothesis by mistake, right? So basically, what we are interested in is this area under the curve. Okay. Any questions? Okay. So from the numbers, we see that, what we have to do is that here we have the population standard deviation, so it's a normal distribution. So this is Z. And we have to calculate Z. So the equation is X bar. The equation is X bar minus mu divided by sigma divided by square root of n. And that is going to be 67 minus 68 divided by sigma was 3.6 divided by square root of 36, and that's going to give us 1.67, right? So we look at the table for 1.67. So the last, very last row, 1.67 gives us 0.047, right? So this is this area under the curve, 0.047, right? So our answer is going to be twice that because this area and this area are equal, right? So 0.047 times 2 is the answer, or 0.09%. Or there's a 9.5% probability of type 1 error, right? And what that means is that if the mean is 68, there is a 9.5% chance that a sample of size 36 has a mean of less than 67 or more than 69. That's the meaning of that. Any questions? Okay. So consider the null hypothesis. So it's the same question. Here the null hypothesis is that average weight of male students in a certain college is 68. The alternative hypothesis represents that is unequal to 68, more than 67 or less than 67 or more than 69. Assume standard deviation of the population to be 3.6. So once the question gives us standard deviation of the population, we know that we have to use the normal distribution, right? And the sample size of 64, and mu of the alternative hypothesis is 70, right? So remember that to calculate the type 2 error, we have to know what's the mu of the alternative hypothesis, or we can't calculate type 2 error, right? Because type 2 error means that some other hypothesis is correct, right? So we have to know what other hypothesis is correct, right? So that's why we have to know what is mu of the alternative hypothesis, right? So what we are interested in is this area under the curve. So this is 67, this is 69, and then so this is the null hypothesis. And then we have the alternative hypothesis, which says that mu is 70, right? So this is 70. So what we are interested in is the area under the red curve. So this is beta, right? So once we draw these two curves, the rest is super easy. The rest is chapter 4 material. Any questions? Okay. So all we have to do is to convert 69 to Z and 67 to Z, right? That's all we have to do. So the equation is going to be 69 minus 70 divided by 3.6 divided by 64, square root of 64. This is going to be Z, and same for the other guy, right? We have to calculate Z for the other guy as well. And we are done. We look at the table. Any questions? So basically what this means is that this is our distribution. This is the correct distribution. So alternative hypothesis is correct, because in type 2 error, we are assuming that the alternative hypothesis is correct. But by mistake, we think that the null hypothesis is correct, which means that our mean is going to be somewhere here, around the mean of the null hypothesis. Right? So basically, we are calculating the probability that the population mean is 70, but our sample of size 64 has a mean of around 68, right? So maybe we can write that down. So what we are computing is beta is the probability that a sample of size 64 from population with mean of 70 has an X bar of between 67 and 69. Okay. So that's beta. That's the type 2 error, right? So type 2 error means that our alternative hypothesis is correct, so mean is 70, but we think that our null hypothesis is correct. We think that mean is 68. Any questions? Okay. So yeah, so after that point, once we calculate Z, what is the value of Z? So the Z that we get, so for this guy, for 69, we get minus 2.2 at the bottom. And for the other guy, for 67, we get minus 6.6, right? So the table doesn't go all the way to minus 6.6. Because of that, we assume this is 0, right? The table goes, the minimum value of the table is 3.99 or minus 4. And that is already quite close to 0. So the probability of this guy will be 0. And then for the other term is minus 2.2. We look at the table, minus 2.2. And I already mentioned this. When you look at the table for negative numbers, this is not the row for 2.2. It's from the other way around. This is the row for 2.2, right? So for 2.2, we have 0.013. Any questions? Okay, so beta is going to be 0.013 because of this number, and the power is going to be 1 minus beta, which is 98%. So that's a very good power. There's only 1% of type 2 error. Any questions? So you can see all of the computers. So for this slide, I also post so you see the solutions also on the slides. So these are all within the slides. Okay, so let's move on. A neurologist is testing the effect of a drug on response time by injecting 100 rats. So N is 100. So immediately after we see such a large number, we know that we have to use the normal distribution, right? With a unit dose of the drug, subjecting each to a neurological stimulus and recording its response time. The neurologist knows that the mean response time for rats not injected with the drug is 1.2 seconds. With a standard deviation of 0.5, the mean of 100 injected rats is 1.05, right? So X bar is 1.05 with the standard deviation, with the same standard deviation, 0.5. Do you think the drug has an effect on the response time, right? So that means that does this drug change the response time from 1.2 second, right? I think it does before even calculating, because 1.05 is quite far from 1.2, right? So to find out how far 1.05 is from 1.2, we have to calculate Z. So Z is going to be 1.05 minus 1.2 divided by standard deviation, 0.5, divided by square root of 100. And that's going to be 3, right? And then we look at the table to see if this is 3, this number 1.05 corresponds to Z of 3. We want to see what's this area under the curve for 3. So for 3, again, we have to look at the last, very, very last row, last column, sorry, and that probability is here, 0.001, right? So this area is 0.001, and all we have to do is we have to multiply this number by 2, 0.001. So it becomes like around 0.2%, 0.3%. And that's a very, very low probability, right? So that means that if your mean was actually 1.2, there's only this number times 2 probability that your sample mean is 1.05, right? And that means that this is actually not your mean anymore. Your mean has changed, right? And that means that the null hypothesis is incorrect with a p-value of 2 times this number. Any questions? Okay, so the p-value is going to be probability that Z is less than minus 3 times 2, and that's going to be 0.002, and that's much, much less than 0.05%. Sometimes that number for alpha to reject is 0.01%, the threshold. So, but anyways, it's much less than both of these. So we reject the null hypothesis with a p-value of 0.27%, with a very low p-value. So this is our p-value. Okay. So a random sample of 100 recorded deaths in Canada during the past year showed an average lifespan of 71.8 years. So this is basically our X bar, right? So this number is our X bar. And this number is our N. Assuming a population standard deviation of 8.9, so this is our sigma. Does this seem to indicate that the mean lifespan today is greater than 70 years? So our null hypothesis is mu is 70 years, and our alternative hypothesis is that mu is more than 70 years, right? Any questions so far? So since we have sigma, we have to use the normal distribution, right? So that means that X bar minus mu divided by sigma divided by square root of 10. That's going to be 2.02, right? And we already know that. Do I have the table here? So basically the number that we got was 2.02, right? The Z that we got is 2.02. And when we look at the table for minus 2.02, we have this probability, right? 2%, right? Yeah.
Why do we look at minus 2?
Why am I looking at minus 2?
Yeah, not 2.02.
Yeah, so that's a good question. So basically, I have to draw here what's going on. So this is 70. And this is what I get, 71.8. Right. So, and I'm looking at the one-sided hypothesis test, right? So I'm only interested in mu being more than 70, right? So that means that what I'm interested in is what's the probability that my actual mean is 70, but I get a sample mean of size 100 with a mean of 71.8 or higher, right? So what I'm interested in is this area under the curve, right? So that's the area that I'm interested in, right? And you can calculate this area as 1 minus phi of 2.02, or you can calculate it as phi of minus 2.02 because the normal distribution is symmetric, same as the student's t-distribution. So for both of them, I can, when I get a positive z, I can look at the negative value because they are symmetric. But I can't do this with the chi-squared distribution because chi-squared is not symmetric. Any other questions? Okay, so so when I look at the table, these two values, let me go to the next. Oops, what happened? Where's the table? I had it. Yeah, here. So it's 0.021. Did I? Okay, so this is 0.021. This is the p-value, right? And we see that the p-value is very small. It's less than 5%. So we can say that we reject H0 with p-value of 0.021. Right? Or another solution for the same problem is that instead of calculating the p-value here, as I did from the table, I compare my z, which is 2.02, to the critical z, right? To z of alpha, right? So since it's a one-sided test, I don't need to do z of alpha divided by 2. It's z of alpha, z of 0.05. So remember, z of alpha divided by 2 was 1.96, right? But this is not alpha divided by 2. This is alpha. So this one you don't need to memorize, but from the table, this number for 5% is 1.64, right? And as we can see, this is much less than 1.96, right? So we say that our z is much more than the z of alpha, and because of that, we reject H0. So both solutions are correct. Yeah.
So the
No, we are using the normal distribution because we have 100 recorded deaths. 100 is a large number. If it's 40 or more, we can use the normal distribution. And in fact, you can actually use the t-distribution for this question. You just get the same answer. It doesn't matter. I don't know if the table for t-distribution has number 100. You know, because for the t-distribution, if I go to the slide that has, where is that slide? So this is for the normal distribution, and we see that the only thing that matters here is z, right? For t-distribution, that's not the case anymore. For t-distribution, in addition to t, we also need the degrees of freedom, like how many samples we have, right? So I don't remember if the table has and the degree of freedom in this case is going to be, since it's 100, it's going to be 99, right? I'm sure the table doesn't have 99 degrees of freedom, right? So actually, even if you want to use the t-distribution, you can't because this number is not in the table.
And how can we know if it's one-sided or two-sided?
Yeah, so that we have to look at the question, like the way the question is phrased. So here the question is saying that, does this mean that the mean lifespan today is greater than 70 years? So if it said unequal to 70 years, it's two-sided. But since it's saying greater, then it's one-sided. Any other questions? Okay. Okay. So a manufacturer of sports equipment has developed a new synthetic fishing line that the company claims has a mean breaking strength of 8 kilograms, right? So this is our mu0. With a standard deviation of 0.5. So since this is something that the company claims, is this S or this is sigma? This 0.5. Yeah, you're right. So this is S, but I mean, this 0.5 didn't actually come from, math or from physics, right? But, this is something that the company claims. So we assume that, they had many, many samples tested, right? So because of that, we assume that this is sigma. This is the population. The question never said that based on 20 samples or based on 50 samples, It never said based on sampling, right? So we don't know how the company calculated this number, right? So we assume that it's sigma, it's not S. But you're right. In real life, we almost never have sigma. We always have S. Okay. Test the hypothesis that mu is equal to 8 kilogram against the alternative hypothesis that mu is not 8. So since the question is saying not 8, then it's two-sided, right? If a random size of 50 lines, so this is our n, is tested and found to have a mean breaking strength of 7.8, so this is our x bar. And here the question says that your level of strength to making a conclusion, your level of significance to making a conclusion is 0.01, so this is our alpha. Right? So basically what we have to do is that we have to look at z of alpha divided by 2, right? Which is going to be z of, so that number divided by 2, so it's going to be 0.005, right? So we have to find this probability in the table, and since this is sigma, then it's a normal distribution. So in the normal distribution for this number, 0.005, the closest number that you find is this one, right? 0.005. And that is equal to minus 2.57. So 2.57. And the z that we compute from the question is going to be z is going to be x bar minus mean divided by sigma divided by square root of n, and that's going to be 7.8 minus 2.83. So we say that minus 2.83 is less than minus 2.57. So basically this is what's going on. This is 0. This is minus 2.57. This is plus 2.57. And the probability that we are here or we are here, so this is our Gaussian curve. This probability under the curve, both of them together, so adding them up is 1%, right? And our z happens to be this guy, 2.83, so we are here. So we are in the rejection zone, right? We reject the null hypothesis. Any questions? Okay. So an agricultural researcher is working to increase the current average yield from 40 bushels per acre. So this is probably our mu, right? So this is the current value. Actually, the question says in the next line, mu is 40. At 0.05 significance level, so this is alpha, he decides to have a null hypothesis of mu equal to 40 against an alternative hypothesis that mu is more than 40. Find the sample size n that is necessary to achieve 90% power at an alternative hypothesis of mu is more than 45, right? So basically what we are interested in is this area. So mu is 45, and this is the incorrect mu, 40. And our range comes from this guy, from the red curve, green curve. So, and our area comes from this other curve, the blue curve. So this is our beta, probability of type 2 error. Oh, actually, no, I think I made a mistake. Yeah, I did make a very small mistake, but it doesn't really matter because this probability is the other guy, as I said in the previous slide, this area, at this point, the blue curve has really attenuated to around 0. So this area after this point is already 0, right? But my mistake is that the alternative hypothesis is that mu is more than 45. So this range is actually only one-sided range. So so this line doesn't exist here. So it's the area that I'm interested in, this area, but it doesn't really matter because this area is 0, right? And anyways, I just drew this. We don't really compute this area because what we want, we have the area, what we want is we want to calculate n, right? The number of samples. So this is the other one is our equation. So basically what we have to do is that we have to use this equation, which gives us n. And remember that we always plug in a positive delta, right? So it's mu minus mu 0. In this case, it doesn't matter because it's a delta squared. Z of alpha. So does the question say what's the significance level? Yeah, 0.05, right? So for 0.05, the closest number that we see is here, right? And that is this row. So this row is 1.64, which we saw before. So Z of alpha is 1.64, and Z of beta. So the power is 90%. That means that beta is 1 minus power, 1 minus 0.9, which is 0.1. So in the table, we have to find 0.1. So here's 0.1 minus 1.28, right? So 1.28. So that's all we need. We have Z of alpha here. We have Z of beta. We have delta, which is 5. Delta is the difference between these two. And sigma is 6.
And assume population standard deviation of 6.
Yeah. So we have everything to plug into the equation, right? So after we plug in the n that we get, so 1.64 plus 1.28 times 6 to the power 2 divided by 5 to the power 2, 12.3. And remember, we always round this number up because if we round it down, that means that the power is a little bit less than 90%. And we want the power to be 90%, right? At least 90%. So n is 13. So we don't really need that many samples, right? With 13 samples, we get a power of 0.9. The reason for that is that there's a large difference between 45 and 40. That's the reason, right? If instead of 45 here, actually we can simply compute that. So instead of 45, if the null hypothesis was, for example, mu, oh, actually there's a mistake here. It should be more. I don't know why. So if the alternative hypothesis was that mu is more than 41, then everything would be the same except for this 5 would be 1, right? So the final answer instead of 13 would be n equal to 13 times 5 to the power 2, 25. So we need for mu more than 41, we need a much, much larger sample size, right? So this is around 300. So n should be 300 if the alternative hypothesis says mu is more than 41. Right? So the power of the test depends a lot on how different is the null hypothesis from the alternative hypothesis. Okay. So the next is when we test on the mean, but we don't know the variance, and we have few samples, so n is relatively small, less than 40, and in these cases we have to use the student's t-distribution. So let's look at an example. Hydro-Quebec has published figures on the number of kilowatt hours used annually by various home applications. It's claimed that a vacuum cleaner uses an average of 46 kilowatts kilowatt hour per year. If a random sample of 12 homes, so this is our n, this is our mu, included in a planned study indicates that the vacuum cleaner uses an average of 42. So this is our x bar per year with a standard deviation of 11.9. So this is our S, because it's quite clear that 11.9 is based on these 12 homes, right? does this suggest at 0.05 significance level that the vacuum cleaners used on average less than 46 kilowatt hour annually, right? So since we don't know sigma, all we know is S, and since our n is small, is 12, we have to use the t distribution, right? And for the t distribution, we have to look at degrees of freedom of n minus 1. So 12 minus 1 is 11. And the question says less than 46. Because of that, it's one-sided, right? So I have to look at z of 0.05, not 0.05 divided by 2, right? And 11. And that's going to be from the table 1.79. Right? So the next thing we have to do is we have to calculate t, and our t is going to be x bar minus mu divided by s divided by square root of n, right? So that means that this is 0, this is 1.79, sorry, 1.796. So if I'm here, I reject, it's 0, right? So all I have to do is to find out where this t is. Is it here or is here? Any questions? Okay, so when we calculate, so our critical t is 1.796, and the t that we calculate is 1.1, right? So it's much less than this number. So we are not here, we are actually here, right? Because of that, we fail to reject H0. Is there a question?
No.
No? That's good. Okay. So the next question is about standard deviation and variance. A manufacturer of car batteries claims that the life of the company's batteries is normally distributed with standard deviation equal to 0.9 year. Right? So this is our sigma. Sorry. If a random sample of 10, so this is our n, of these batteries has a standard deviation of 1.2, so this is our S, do you think that S is more than 0.9? Right? So the company claims that S is 0.9, right? And we test 10 samples, and we get a standard deviation of 1.2, which is, much more than 0.9. Right? So do we trust the company, or we say that S is actually more than 0.9? Right? So the null hypothesis would be sigma is equal to 0.9, and the alternative hypothesis will be sigma is more than 0.9. Actually, there's a mistake here. This should be sigma, right? Because S is 1.2. We know what S is. And use a 0.05 level of significance. So since this is about, so for variance, it's really easy. There's only one distribution that we can use, and that's the chi-squared distribution, right? So our statistic is going to be n minus 1 times s squared divided by sigma 0 squared, right? And we can actually look at the table to find the significance level of 0.5. So since it's one-sided, actually for the chi-square, we never divide by 2. So, so here, since chi-squared, we don't divide by 2, so we have to look at 0.05. 0.05. We have n equal to 10, so I have to look at n minus 1 equal to 9. So this is my n minus 1. And the intersection is this point, right? So 16.92, right? And now all I have to do is that I have to compute this value and see whether this is more than 16.92 or less than 16.92, right? So this value is going to be 10 minus 1 times 1.2 to the power 2 divided by 0.9 to the power 2, right? So I calculate my x0, and the chi distribution looks like this. So this is 16.92, and that means that this area under the curve, how much is this area? After 16.92, 4 degrees of freedom of 9. So this is a chi-squared distribution for n minus 1 equal to 9. What is area under the curve after 16.92? What is this area? 0.05, exactly. So this area under the curve is 0.05 because we got this number from the table here. So if we are here, we reject the null hypothesis, right? So if this guy, x0, happens to be somewhere here, we say that that's very unlikely for sigma, for s to be here, right? Or in other words, there is a 95% chance for s to be here, and there's only 5% chance for s to be here. Okay. So all we have to do is that we have to plug into this equation, and the number that we compute is 16.0, right? So it's a little bit less than 16.92, so we reject the null hypothesis. Sorry, we fail to reject the null hypothesis. So there's no strong evidence to suggest that the company is wrong. So we see that we actually do need these tests because just by looking at the numbers, it's hard to say whether 1.2 is very different from 0.9, right? But we see that, there's a high chance that, your S is 0.9 if your true sigma is 1.2. Any questions? Oh, before I forget, there was something about the project. I get these questions a lot that, n, like number of samples in your project, right? So every year this comes up. So, if you're counting the number of, for example, people who enter Tim Hortons at a certain time, right? And let's say you count them from 9 a.m. to 10 a.m., right? And let's say you get, 100 people. That's not your n, right? 100 is one data point, right? So if you count the people from 9 to 10, and the number is 100, 100 is not n. Your n is actually 1. You only have one sample, right? So n is the number of experiments that you do, right? So n will be like how many times you repeat this experiment, right? So in one day, you go from 9 to 10, and you count, and it's 100. The next day, again, you go from 9 to 10, you count the number, then your n is 2. Then the next day, you go. So if you want to increase your 10, it's probably not a good idea to look at 1 hour duration, right? Because it takes a lot of time to collect, 40 data points, right? So what you can do instead is perhaps to look at like a 15-minute window, right? And that will increase your n. Yeah.
So for example, we didn't do a time, like I run to that issue, so instead of dividing into the time interval, we divide into like a set amount of people, so it'd be for every 30 people. Does that still work, or?
Can you say that again?
So instead of looking for a 10-minute interval, our interval is set with like 30 people.
Mm-hmm.
So that would be.
Yeah, that's okay. So it depends on what is your hypothesis, right? So you can look at, instead of saying that I'm going to count how many people enter in every 10 minutes, you can say that I'm going to, measure the time until it takes for 30 people to show up. That's okay. And then your samples, your random variable then will be t, which is a continuous random variable, and that's fine, right? So that's the difference between Poisson and exponential distribution. Both of them are fine. So in one case, you can count the people and say how many people enter in 10 minutes. In the other case, you can say how long it takes for 10 people to show up, right? So in the second case, your t will be an exponential distribution. Yeah.
Is n supposed to be bigger than 50?
No, you don't need to have, So for example, if your yeah, it's going to take forever to collect, 30 data points, because that means that if your duration was 1 hour, it just takes 50 hours to, collect the data, which is a long time. So your n can be like 8, right? So then you use the t distribution because your n is few and you don't know anything about your population, right? So that's okay. You can have n of 5. As long as you use the right distribution, you don't need many data points.
Okay, cool.
Yeah. Yeah. So, but the important thing is that if you wait for an hour, let's say you waited for an hour twice, once in the morning and once in the afternoon. And in the morning, you get 100 customers. In the afternoon, you get, 110. 100 or 110 is not n, N is, in this case, is 2. Yeah. Any other questions? And remember that we have a POD for this course, and the POD means that basically his job definition is to help you with the project questions. So you can ask any questions. Okay. So actually, we are out of time. Oh, this was actually the very last question anyways. So perfect timing. All right. So